This is PHY1020, Conceptual Physics Week 3, Conservation Laws, Part 2. So we discovered the concept of momentum and momentum conservation. Let's discuss this with a few examples to improve your understanding of these concepts. And let's see how we can use this notion of law of conservation to try to analyze what's happening, for instance, in a car collision. So let's consider that we have a car number 1, with a mass of 1,000 kilograms, running into the rear of a stopped car number 2, that has a mass of 1,500 kilograms. And with the speeds that are shown below. So the car number 2, the black car, is originally at rest, whereas the car number 1, the red car, is incoming at a velocity or speed v sub b. Right? And what we are going to be told is that, well, the red car smashes into the black car, and then together they end up going at a velocity of 4 meters per second. So let's assume that indeed the two cars are, right after the collision, the two cars are somehow jammed together for whatever reason, and now that they are moving at 4 meters per second. Now let's be clear. If you have experienced a collision, you know that right after the collision, a motion will persist. You know, you're smashing into a car, and then your car stops, but you know you are actually the two cars will actually keep moving a little bit, right? And here we're assuming that they keep moving at 4 meters per second. It's quite clear that, being the fact that those two cars on the road, there's going to be some friction, and they're not going to go at 4 meters per second forever. They will eventually stop on their own device. But what's important is that right after the collision, right after the red car smashed into the black car, now they're hooked together and they go at 4 meters per second. So the question we ask ourselves is, what was the car number 1 speed before the collision? This is a situation that happens all the time. A person might be distracted, a person might be driving too fast, and they don't see that the car in front of them is stopped at a red light, for instance, and then boom, they smashed into the car. So such things can happen, and in fact do happen quite often. So how do we proceed to calculate the velocity of the red car just before the collision? We're going to use the conservation of momentum, the principle or law of conservation of momentum. This law tells us that the total linear momentum of the system is constant. So that means that the momentum of the two cars before the collision must be equal to the momentum of the two cars right after the collision. So the total MV before is equal to total MV after. Now, before the collision, only car number 1 is moving, whereas car number 2 is stopped. So the total linear momentum before the collision is just the momentum of the first car. So MV before is M1 times the velocity of that car before the collision. Whatever that, we don't know what that, this is the value we're seeking. We don't know what it is, so I'm going to label it or call it V before. So M1 times V before is going to be 1,000 kilogram times V before, 1,000 kilogram being the mass of vehicle number 1. After the collision, both cars are moving together as one body, at least for a short amount of time. So after the collision, MV is M1 plus M2, the two masses, the two objects, moving together at the same speed, v after, v underscore, v sub index after. So M1 is 1,000 kilogram, M2 is 1,500, so that's 2,500 kilogram times V after, and we're told that V after is 4 meter per second. So 2,500 kilogram times 4 meter per second, that is 10,000 kilogram meter per second. That's the momentum after. And momentum conservation tells us that the momentum before the collision is equal to the momentum right after the collision. So what we saw before, 1,000 kilogram times V before, is now equal to 10,000 kilogram meter per second. That's the momentum after the collision. So then we can solve for V before by dividing on both sides by 1,000. And we find that V before is 10,000 divided by 1,000. That's 10 meter per second. 10 meter per second is quite fast. And so there's a chance that whoever was driving was perhaps exceeding the speed limit, or at the very least not paying attention to the road. Let's consider a second example, that of a rocket ejecting gas at the rate of 10 kilogram per second. Right? So to be clear here, what is propelling the rocket is the ejection itself. It's not the gas hitting something. It is the gas being pushed out of the rocket at a very high speed and a very high rate or mass rate, if you will. So the mass rate here is 10 kilogram per second. Let's assume that the gas is very quickly reaching a speed of 100 meter per second. So we now have an amount of gas of 10 kilogram per second leaving the rocket at 100 meter per second. So now let's assume that initially the rocket had a mass of 50,000 kilogram. We can ask ourselves, what is the speed of this rocket after 200 seconds? Right? So now we have to think a little bit, because we know that we cannot strictly apply F equal ma, because the mass of the rocket is not changing. As the mass ejects gas to accelerate, its mass is constantly decreasing. However, we can use the notion of change in momentum being caused by the ejection of gas, a certain amount of gas per second at a certain speed. So let's see what we can do with this. So let's apply conservation of momentum. We have that the total amount of gas expelled from the rocket will have had a certain amount of momentum, a change in momentum. So essentially, you can think of the gas going from rest relative to the rocket to some high velocity. And so that means that the gas is changing momentum. And it is this change in momentum that will cause the acceleration of the gas, and in turn the acceleration of the rocket. So we will calculate in a moment the momentum change, the change in momentum of the gas. That will be then also equal to the mass of the rocket times its change in velocity, and so we have a rocket with sorry, let me take a step back here. We saw that the rocket is ejecting gas at a rate of 10 kilogram per second, right? And so it means that per second the rocket is ejecting 10 kilogram. So each second that passes by, the rocket ejects 10 kilogram. And so in 200 seconds, the rocket will eject 200 times 10 kilograms. So that is 2,000 kilogram. So that's what I've written here. The rocket overall will lose 2,000 kilogram by expelling 2,000 kilogram of gas over a period of 200 seconds. And the gas is expelled at a velocity of 100 meters per second. So the change in momentum of the gas is 2,000 times 100. That's 200,000 kilogram meter per second. So over this time of 200 seconds, the rocket will have gone from 50,000 kilogram minus 2,000 kilogram. So at the end of the 200 seconds, it will be now 48,000 kilogram. The momentum gained by the rocket is the momentum imparted to the gas. So that means the rocket itself has gained a momentum corresponding to 200,000 kilogram meter per second. At the end, the rocket is weighing 48,000, so the velocity at the end of these 200 seconds will be 200,000 kilogram meter per second over 48,000 kilogram, and that amounts to 4.167 meter per second. So we first computed the momentum imparted to the gas and how much momentum was carried by all the gas that was expelled in 200 seconds. Once we had this momentum, we equated this momentum to the momentum gained by the rocket in the same amount of time. And then we computed the mass left in the rocket after it had expelled gas for 200 seconds. And so then we computed the final velocity of the rocket as 4.167 meter per second. Let's consider another example. This one is a 10,000 kilogram truck traveling at 12 meters per second. Let's assume it hits a 2,000 kilogram car standing at rest. You have this massive object, a truck, 10,000 kilogram, hitting the car. The car will then be pushed ahead and will be basically pushed ahead, moving and at some maybe not so small velocity. The passenger of the car will most likely have a whiplash in the process. So let's also assume that the truck is seen to be moving at 9 meters per second right after the collision. So the truck went from 12 meters per second to 9 meters per second. So hitting the car was not sufficient to stop the truck, right? So the truck was going quite fast, hits the car, and even after the collision, the truck doesn't stop. It only slows down to 9 meters per second. And then we can ask ourselves, how fast is the car moving at that time? So here I will let you try to figure out the speed of the car right after the collision. So you apply, I'll give you a hint, you apply momentum conservation. Momentum before and must be equal to the momentum after. I told you the mass of the truck, the mass of the car, how fast the truck was moving before, and how fast the truck was moving after. I also told you that the car was at rest before the collision. The only thing that you don't know, and that's the quantity that you seek, is the velocity or speed of the car right after the collision. So take a pause and try to figure this out. You will find that it's 15 meters per second. Let's consider another example. Let's think of a metal ball that we let go from the top of a building, and this ball falls towards the ground. So it starts, we let go at 0 speed, and it just accelerates downward towards the ground. Let's assume the ball has a mass of 0.5 kilogram, and that we can ask then, what is the momentum after 10 seconds? We will ignore friction, and we will assume the acceleration is due to gravity only, no friction, and you know that the acceleration of gravity is 9.8 meters per square second. So what is the momentum after 10 seconds? There are many typos here. I apologize for this. K for kilo should always be lowercase. I will give you let's make a pause and let try to figure this out. So you should have found a value of 98 kilogram meter per second. Let's consider another example, that of a rocket ship burning off 1,000 kilogram of fuel that was ejected at 100 meters per second. What is the speed of the rocket if it originally had a mass of 3,000 kilogram? Go back to what we did a moment ago to figure out this problem. And let's make a pause, and you try to figure out the value and answer the question. So you should have found that the speed of the rocket at the end is 50 meters per second. Another example, that of a truck, 10,000 kilogram truck traveling at 12 meters per second. It hits a car and then, I think we already did this, so let's skip. This we did also, let's skip as well. And so, a satellite has been placed in a steady orbit around Earth. Let's say that the radius of this orbit is 10,000 kilometers. And it's a circular orbit with a constant speed. We're not told what speed it is. We're told that the satellite has been going in this orbit like this for many years, several years, without change in speed, mass, or radius. What is the momentum of this satellite along its orbit? Is this linear momentum conserved? Not conserved? Will it be conserved after a while? Or was it initially conserved but not anymore? Or maybe we don't have enough information to tell. What do you think? I'll let you answer the question. The momentum is not conserved. You might ask, why? Why is the momentum not conserved? We just discussed for 1.5 lecture now that momentum is a conserved quantity. It is a conserved quantity indeed when there is no external force on an object. But if you have a satellite in orbit around Earth, for instance, the pull of gravity is a net force applied onto the satellite. So there is a non-vanishing, non-zero net force onto the satellite. It is this force that accelerates the satellite and keeps it in orbit on a circular trajectory, or approximately circular trajectory around Earth. And we'll now stop here.